I think I restart numbering with chapter 2, so I'm going to say chapter 1. And then we can look at individual questions. So for number 1, which of the following is an example of a quantitative observation? Remember the difference between quantitative and qualitative.
Numbers versus like an observable like difference.
Right. Just a general observation is qualitative. Quantitative observations always have a number associated with them. So the best answer for that one would be D. The temperature of the liquid is 60 degrees. Yeah. Okay. I'll just leave them up there until I need the space. Number 2, generally observed behavior that can be formulated into a statement, sometimes mathematical in nature, is called
Theory.
It's either theory or a natural law. Yeah, because we're not trying to explain why. It's just generally observed behavior. So that would be a natural law. D again. All right, skip a few. The 4 metric prefixes, order them from smallest to largest. So it looks like we got the same ones in each one. So if we pull them out, nano, milli, centi, and kilo. This is 3. Nano, milli, kilo, centi. Centi and kilo. Now, there are a lot more than that. These are just the ones that are given in this particular question. What does nano mean as a prefix? How does it modify the base unit? Times 10 to the minus 9th. Yep. So it'd be
Very small.
you're right. Milli is a little bit bigger. 1,000th. Centi. Right. Hundreds. Yeah. Let's see. Deci is tenths. And kilo is 1,000 times. Okay. If we're going from what? Smallest to largest, right? That's smaller than that one, smaller than that one, smaller than that one. So our answer is A. It's the first one is correct. That's as long as we don't cheat and look at the answer. All right. Well, let's make some room. Praise it too well, and I just sprayed it with WD-40. Number 6. Okay. 8.1 kilograms is how many grams? This is a very simple unit conversion.
8,100.
Going to grams. Right. Now you can, if you know what kilo means, you have 2 possibilities here. Right. If we do dimensional analysis, then we would want to cancel the kilograms. So I'll put that denominator for the numerator cancels. This is equal to how many grams? Right. 10 to the 3rd, right? 1,000 grams. Then you get 8.1 times 10 to the 3rd grams. But a simpler way would just be, what does kilo mean? Kilo is 10 to the 3rd, right? So this is the same as that. And there you have it. So that's B. And then we'll go ahead and do 7. 0.3980 meters. Is how many millimeters? So we need a conversion factor that will get rid of the meters and leave us with millimeters. So millimeters, how many millimeters in a meter? 1,000. 1,000 millimeters. So 1,000, let's see, is this in Some of them are scientific and some of them are not. Well, let's try it both ways. If we move this, which way are we going to move the decimal?
To the right.
Yeah, because the unit's getting smaller, the number has to get bigger. That's the clue. And so go to the right 3 places, and we get 398 kilomillimeters. I think that's one of the answers. Yeah. All right. Number 9. What's the measure of resistance an object has to a change in its state of motion?
Friction.
Okay, suppose I give you a frictionless environment. What would it be then? Key word here is inertia. What gives a substance inertia? It's mass, yes. Right. That's also A. So how is mass related to weight?
Gravity pulls down on something like harder on something that has larger mass.
Yes, that's true. If you have the same mass, but different weights, what does that tell you?
One's denser. So
No, they have the same mass.
Oh.
Doesn't matter. Density doesn't matter. They have exactly the same mass, but one weighs less than the other. They have to be in 2 different gravitational fields. Right? So if I'm on the surface of the Earth, I weigh about 200 pounds. If I'm on the surface of the moon, I'm about 1/6 of that, which would be to 6. Well, yeah, 6 to 200. So about 33 pounds. Yeah, be a lot lighter. So weight is a measure of force. Mass is a measure of absolute substance. The only time that mass is not constant is in black hole, near a black hole. Then all bets are off. All right, number 11. So we've got these 3 trials. We got a 1 gram. We know it's a gram, right? It's a standard mass of 1 gram. And we've got these 3 trials, and we measure on our balance 1.201, 1.202, and 1.200, plus or minus 0.001. So we know the true value is 1.00 grams. These are all grams. Okay, what can we say about this in terms of accuracy and precision? I'm sorry? Right, it's inaccurate, but it's precise. These numbers are very close together. They're grouped close. But it's way far away from them. So it's not accurate, but precise. Okay. The other clue is that the instrument that you're using, we know will give us a value within 1,000th of a gram. Okay, these balances over here will give you within 1,000th of a gram. And if you say plus or minus 0.001, that means this is either 1.200 to 1.202. That's the range that's permitted for that measurement. So these two fall within that range. That tells you something about the precision. But the accuracy, we're off by what? An average of 0.001. I mean 2.01. So we're high by 0.201, plus or minus 0.001. We're off by that much. And it's almost the same amount for each one. This is what's called a systematic error. In other words, it's this roughly the same error every time. Those are good kinds of error because you can correct for them. It's like when you're sighting in your rifle for hunting season. Right? The systematic error, if you've got a grouping that's off the target, like that, there's your bullseye. Then you know if you dope your scope just right, you can bring that whole group right down on the bullseye. That's a systematic error. A random error is like, if your gun's shooting like that, there's no way to correct for that one.
Maybe a user error.
It could be, yeah. Right. You gotta shoot between heartbeats, right?
Yeah.
Okay, so the answer to that one is C. So to correct for random error, that's where we bring statistics in. That helps us manage random error. Okay, here we have our famous targets. So E says, which of the following figures result have high precision? Let's see, 12. High precision, that is good grouping. Two of them, right? 2 and 3.
Yeah.
So that's E. The next one wants to know which of the following is correct. Okay, so now we have to say, all right. A says figure 1 represents systematic error, figure 2 represents random error. It's the other way around. 2 is systematic, 1 is random. So it can't be A. Figure 1 represents random, figure 2 systematic. Okay, B is correct. Yeah. Let's see, we'll skip a few. There's lots of repetition in here. 16. The amount of uncertainty in a measured quantity is determined by. All right. We didn't go into a lot of detail about this one in class in the lecture. When you're making a measurement, it's like, what's your name again?
Ethan.
Ethan. It's like Ethan said, it could be a user error. Right? So when you're making a measurement in the laboratory, you have possibility for error from the machine itself or the measuring device. Then you got possible error from the user. So both of them enter in. You want a machine that's as accurate as you can afford, and you want to know how to use it. So both the skill of the observer and the limitations of the measuring instrument are play into uncertainty of that measurement. 17. Let's keep going. 17. A scientist obtains the number 0.0500, 0.0500, right? No, 45. I did that last time. Not in here. I did it for another class. Left the 4 out. 0, 4, 5, 0, 0, 6, 7, 0, 0. That's the number you're given. You're only allowed 4 significant figures. So where do we start? Start from the left, right? But we don't include these because they're not significant. So we have 1, 2, 3, 4. So we look to the right of that one. This is greater than 5. So that's 0, 4, 5, 0, 1. Should be our correct answer. That'd be E. Oh, this brings up another problem I have with, I have some students, not a lot anymore, but some students come to me and they would write that number 0.04501. And I count it wrong. That's an orphan decimal. Right? It only has one parent on this side. It needs both of them. You need to bracket in those decimals. Okay. For one very simple reason. If this is in a list of numbers, then you know what the decimal's there for. But if it's in a sentence, you might mistake that decimal for a period at the end of a sentence. It's just for clarity. So always bracket in those decimals with a 0. All right, 20. Let's make some room here. Express the number 0.0810. 0.0810 in scientific notation. Okay. We need the coefficient between 1 and 10. So the only way to get that is to move to the right, correct? When you move to the right, you're storing up negative powers of 10. Right? Because it's a small number here. We're going to make the number bigger. So that means the power of 10 has to be smaller, minus 2. Okay. And then ask yourself, can I convert that back into this one? Right. If this is 0.01, 0.01 times that should be this. Okay. 21. Let's see, that was D. 21. Express this number in common decimal form or standard notation. 6.49 times 10 to the minus 3. And when you do the conversion, you preserve the significant figures. This one has 3. 1, 2, 3. This one has 3. We want to convert this one. So what we need is, we know we're going to go to the left because that's a negative number. I just put a bunch of zeros out there so we can have, we're going to move 1, 2, 3. Right, we don't need that one now. So that should be the number, 00649. That's A. Okay. Let's see, I got room for 22. So this one's going to go the other direction. 237 times 10 to the 4th. This needs to be a bigger number than that because this is positive powers of 10. So 2, 3, 7, put some zeros out here. We need to move 4 places. 1, 2, 3, 4. That's not right. 3 significant figures? I just gave it 6. There we go. Now we've only got 3 significant figures because there's no decimal in there. Trick question. D. (23) We generally report a measurement by recording all the certain digits plus how many uncertain? 1, yeah, the very first, farthest one to the right is the uncertain digit by convention. Right. Okay, you're asked to determine, see, 24. You're asked to determine the perimeter of the cover of your textbook. You measure the length at 39.36 centimeters. That is one huge textbook. All right, centimeters like that, 40 of them would be, that's a big textbook. Must be an art class. But the length is 39.36. 39.36 on both sides. If we're doing the perimeter, we need two of these and two of those at 2483 centimeters. Right. So if we want to know the perimeter, we need 39, 36, 39, 36 for the other side, and then 2483 twice. Okay, and the question is, the sum of these numbers has how many significant figures, and the product of these numbers has how many significant figures? Oh, no, I'm on the wrong one. 24, sorry. How many significant figures should we report? Well, this is the addition subtraction rule. So you have to line up the decimals and just add them together and see what you get. All right. So that's 18, carry the 1. That's 16, 17, 23, carry the 2. And that's 8 and 18 is 26, 28, 2, 4, 6, and 6 is 12. Okay. So we lined up the decimal. These are the uncertain numbers. We can keep all of them. We have 5 significant figures in the answer. We started with 4 and we ended up with 5. Okay. And 20, did I put the right numbers in there? Yeah. $25. Consider these numbers. 23.68 and 4.12. One question is the sum. What's the sum? How many significant figures in the sum? 2, right? 4 significant figures in the sum. Okay. When we multiply them, you're only going to have 3, right? So you have 4 and 3 is your answer, which would be D. Now, why are we bothering with these significant figures? Remember the whole reason for this rigmarole? So we can be honest with ourselves about the outcomes of calculations. Because we know we can't get rid of an uncertainty. We need to accommodate it some way. And this is how we do it. All right. So we're going to subtract these two numbers, 27. 4.0021 and subtract 0.179, 0.179, and see what the answer is. All right, 0 from that's 1, 3, see, yeah, 7 from 9 is 2, and 1 from 9 is 8, 3. But This is the uncertain number for that one. This is the uncertain for that one. So we're stuck with this one. So we have to do 3.823. That's it. 3.823. Because if we put anything else down there, we have to round this one based upon that one. But that's still 3.823, which would be A. All right, now we got a compound calculation. Let's see, 32. So what do we got? 3.478 times 1.164 grams divided by 2.00 milliliters minus 0.169 grams per milliliter. Right. Order of operation. PEMDAS says parentheses first. So we do these first and divide by this one. And as far as the calculation goes, you can do them all together. Right. Parentheses, exponents. We don't have any exponents. Multiply, divide. So we can do these and those together. And the answer, we can't move over here yet because we have to get this operation done. It's two sets of rules. So 3.478 times 1.164 and divided by 2. Okay, my calculator says 2.0242 grams per milliliter. How many can we keep? Only 3, right? Right. So we're stuck with that one. This is 2.02 minus 0.169. So 9 from 0 is 1, 6 from 11 is 5, 1 from 9 is 8, and 1. And we're stuck with this one, like that. So we have 1.85 grams per milliliter. Okay. You have to do it that way when you got mixtures. Okay. 35. Express this volume, 781.2 cubic centimeters in liters. Right? What do we know about cubic centimeters?
It's a volume, like.
Well, we use this for solids. We use milliliters for liquids. But what's the relationship between this unit of measure and liquid unit of measure? They're exactly equal. 1 cubic centimeter is a milliliter. Right? So we can save ourselves some effort. Just call that milliliters. Then we can get rid of milliliters and leave us with liters. We have 1,000 here. Right? So if we bring that into the numerator, now it's 10 to the minus 3. 781.2 times 10 to the minus 3. Let's see, our answer is in standard notation. So 1,000th of this would be 1, 2, 3. Like that. Oh, wait a minute. Yeah, that's right. 4 significant figures. D. Okay. $37. The pressure of the Earth's atmosphere at sea level is 14.7 pounds per square inch. Pounds per square inch. We want to convert that to grams per square meter. When you have when you're converting a complex unit of measure, do one part at a time. So let's do pounds first. We want to go pounds to grams, right? We have a relationship there that's given pounds to kilograms. Okay, we can do that, which is 2.205 pounds. 1 kilogram. Got rid of pounds. Now we need to go to grams. So we get rid of kilograms. Notice I put them top, bottom, so they cancel. Leaves me with grams. So this is 1,000 grams per kilogram. So now we got grams covered. Now we're going to chain our conversion for square inches. So 1 inch is 2.54 centimeters. So I need inches on the top and centimeters on the bottom. What's wrong with this picture? That's not squared. This is only going to cancel one of those inches. So here's the solution. Square the whole thing. Right. 1 inch squared is 2.54 squared centimeters squared. Okay. Furrow brows. Okay, so now we got square centimeters on the bottom. Now we need to convert centimeters to meters. So we need square meters on the bottom, centimeters on the top. This is 100 centimeters in a meter. Do the same thing. Right? That's been squared. We need to square this and leave us with square meters. So that gives us our bottom unit. Now what do we do? Well, since it's all multiply, divide, you can do it in any order you want. I usually go straight across, multiply, 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 and then come back and divide, 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 divide. So 14.7 times 1,000 times 1 squared times 10 squared, 10 squared squared. 10 to the 4th, right? That's 10,000. Then I go back, divide by 2.205, and divide by 2.54 squared. And that's it. So scientific notation. All right. So my calculator says 103335354. All right. All conversion factors are exact numbers. They don't limit your number of significant figures. Only the starting number does. So 14.7 has 3 significant figures. We're limited to this one right here. So we're going 1, 2, 3, 4, 5, 6, 7. But only 3 significant figures. 1.03 times 10 to the 7th. That would be B. These, when these conversions, well, for any problem, when any problem gets complex, you gotta get really regimented methodical about your approach. Otherwise, it's just going to flood your brain and bring your brain to a screeching halt. So have the methodology in mind and then work it step by step. This one was fairly simple, actually. Later on, we'll probably get problems where you actually have to split the problem into 2 or more parts, work the parts, then bring those answers back together to get the final answer. Those are the ones that are real brain scratchers. Because then you have to really be careful about your methodology. But I'm not going to just spring them on you. You're going to have methods to draw upon. Okay, 41. The density of liquid mercury is 13.6 grams per mil. So that's quite a bit less dense than osmium is. What's the density in units of pounds per cubic inch? So here we go again. We've got a grams per milliliter, and we want to convert it. So we're going to do one at a time. I'll do grams first. We're going to pounds per cubic inch. I'll put this out here as a reminder. We're headed for pounds with grams. Our conversion factors are given as kilograms. Okay, grams, we have to have kilograms first before we can use that conversion factor. So we need 1,000 grams per kilogram. All right, that leaves kilograms. Now we can go pounds. 2.025. No, 205. 205. There we go. Pounds per kilogram. So the kilograms are gone. Got our pounds right here. And now we want to convert milliliters to cubic inches. So we know that a milliliter is a cubic inch. Is a cubic centimeter, excuse me. Is a cubic centimeter. So we need how many centimeters in an inch? 2.54. And that one has to be cubed to give us a cube here to cancel out. And that should do it. That would give us cubic inch. Right. So in the interest of time, we should get an answer 4.91 times 10 to the minus 1. We do the calculations. 3 significant figures, 3 significant figures. One, let's see, skip to Malou, 46. All right. So if I haven't said it before, what's the primary purpose of word problems? To confuse. They're designed to confuse the reader so that if you are confusable, that means that you really don't have a good handle on the topic. So they might put a lot of stuff in there that you don't even need. I call it blue smoke. Like a car that needs an engine that needs rings or valves replaced. Right? They blow a lot of burn oil out. Blue smoke. During a physics experiment, an electron is accelerated to 93% of the speed of light. Speed of light is 3 times 10 to the 8th meters per second. So 93% of that is our starting point. And we want to convert it to miles per hour. So 3 times 10 to the 8th meters per second. 3 times 10 to the 8th meters per second. And we need 97% of that. Right? Multiplying by percent doesn't make sense. Percent is a dimensionless number. But this fraction is usable for the calculation. 0.97 is equivalent to 97%. So once you got that number, now we can start converting units. So we want meters to miles. Right? What's our conversion? We have kilometers to miles. So we need meters converted to kilometers first.
97% or 93%?
Oh, yeah, you're right. 93. Sorry. Yeah. Don't let me get away with these things. Okay, now we can convert kilometers to miles. Kilometers on the bottom, miles on the top. And the ratio is 0.6214 miles. 0.6214 miles. That's why when the Olympics switched from miles to the metric system, or did they do that? I think they were always metric. But in this country, we raced miles. Like, who was it that was the first one to break the 4-minute mile? Long time ago. Can't remember his name. Anyway, they needed a unit for part comparison of the mile to the meter. So they chose 1,500 meters. So 1,500 meters is going to be, let's see, 1,000 meters is 0.6 of a mile. So add another half to that. That's about 0.93. So they're close to a mile. So 1,500 meters should be run a lot quicker than 4 minutes, and they are. There was this kid in my high school. I didn't play football because I didn't want to get my head crushed. So I was on the track team, the soccer team. And then we had this one kid on the track team who was blazing fast in the mile. I'm pretty sure he broke 4 minutes. But the odd thing was he was a chain smoker. How do you do that? He had the right kind of twitch muscles. Right? Not the fast twitch, but the slow twitch. So they just keep going and going and going. And he could maintain that speed for the whole mile. It always amazed me. You'd see him outside huffing a cig every half hour or between classes. And then he'd go out on the track and just blow everybody away. Okay, so now let's see. This is miles. Miles. Okay, that gives us miles. Now we need to convert to hours. So we got seconds. Does anybody know how many seconds are in an hour? 60 seconds in a minute, right? 60 minutes in an hour. 3,600, yeah, 3,600 seconds in an hour. So that gets rid of seconds and leaves us with hours, miles per hour. So if we multiply all that stuff out, we should get 6.2 times 10 to the 8th. Now, I'm thinking that the authors of this question say that we only have 2 significant figures because of that number right there. But I don't know. I guess it's arguable. We could keep 3. $49. I'll start erasing from this side in case you're still writing. $49. What do we have here? 1928. Who cares, right? 29.3 grams of a new element was isolated from 660 kilograms of the ore molybdenite. I wonder what that element could be. Molybdenum, right, up there on the table, under chromium, MO, molybdenum. I'm sure that's what the element is. The percent by mass of this element in the ore was. So we know how to do percent by mass. 29.3 grams of the element divided by the same unit of measure. We got 660 kilograms. 660 kilograms. We need to convert that to grams. There. So get that one converted, then divide it into that times 100. Okay. This percent by mass only works if the grams in the numerator, if the units in the numerator equals the units of the denominator. And we should end up with 0.0044%. And that's because here, only two significant figures. We're going to look at temperatures conversions. $50. So 409 Kelvin equals what? Oh, we got several choices, Fahrenheit and Celsius. So where do we have to go first anyway?
Celsius.
Yeah, we have to go to Celsius before we can make Fahrenheit. So let's do that one and see if any of those Celsius match up, and then we can save ourselves some time. So what do we do?
Gonna cancel out Kelvin, so Kelvin Celsius.
Remember, K equals C plus 273. So C would be K minus 273, wouldn't it? And we can do that because the size of their degree mark is exactly the same. So all we have to do is shift the zero. And this is how we shift the zero mark. So what's that? Let's see, 136 degrees C. That's D. Save ourselves some work. All right, melting point of a certain element, 391 degrees C. What's the Fahrenheit? Okay, this one we do have to use the Fahrenheit conversion. So we have 391 C. What's the formula? The one I have memorized is F equals 9/5 C plus 32. And let's see, we're starting from C, so that would be a good choice. Otherwise, you have to solve it for the other one. So let's see, 9/5 of, what was it? 391 plus 32, right? And that should equal to 736. Now, does that make sense? That's about 2 times this, which would be 750 in the neighborhood of 700 something. Yeah. Okay. Just estimate to see if we're in the ballpark. $54. We're still in chapter 1. How are we doing on time? We've only used an hour. That's good. In 1984, again, who cares? Some drums of uranium hexafluoride were lost in the English Channel, which is known for its cold water, about 17 degrees Celsius. Yeah, it's cold. 20 degrees is 68 Fahrenheit. So we're down another 3 Celsius would be another degree, 66. and a half maybe. Fahrenheit's cold. Melting point of uranium hexafluoride is 148 degrees Fahrenheit. So the melting point is 148 degrees F. And the temperature of the water is 17 degrees C. So what we have to do is say, is that temperature greater than this value? Right, to see if it melts. So if we put, if we say C, and we say F equals 9/5 C plus 32, that means F minus 32 times 5/9 equals C. Or we could do this one. Let's do this one. It's easier. So 17, what's 1.8 times 17? It's about a little less than 30. 30 plus 32 is 60. All right. So that temperature is a lot lower than this. It's not high enough. We don't even have to calculate it, just estimate it. Right. So this is going to be a solid, or uranium hexafluoride. Hexa, 6. Why do they even do that? Why do you make uranium hexafluoride? Have you ever, well, it has to do with the way we purify or the way we concentrate U-235. There are a number of methods and they all involve gases. Right. You got gaseous diffusion. You got centrifuges, gas centrifuges. Right. Those are the two most popular. And the boiling point of uranium hexafluoride is a lot lower than pure uranium. So we convert it into a fluoride, you can get it into a gaseous state with less energy and on your way. So that's A, solid. How about, ooh, this is a fun one. I have to remember some geometry for this one. 56. A monolayer containing 3.23 times 10 to the minus 6 grams of oleic acid. Ever heard of oleic acid? It's a fatty acid. I think the Latin for butter is oleum. So oleic acid comes from that. Anyway, I'm just guessing. Don't take me literally. We know we have this many grams of oleic acid and we drop it in water. And the fatty acids have a dual personality, so to speak. Fatty acid has one end that's hydrophilic. And then has this long chain, hydrocarbon chain like that. And this is hydrophobic. Okay? So if you drop it on water, it's going to be, this end is against the water, and this end is sticking up above the water. All right, and they line up that way. This part, the tail of oleic acid, the technical term is they dissolve in one another. So you get this, if you turn it on its side, then you get this monolayer, which is the length of the molecule. So if we look at it in terms of a cylinder, right? Cylinder like this, what we see is the heads against the water like this, then their tails up here like this. This is the height of the cylinder. The length of the molecule is the height of the cylinder. So we have this monolayer of these oleic acid molecules. And we're also given the area of that cylinder is 20 square centimeters. Okay. So we're looking for what? The thickness of the monolayer, this height. So what's the volume of that cylinder? It's height times area, isn't it? Volume equals height times area. We know area. We want to know H. So we got to find the volume. What's the volume occupied by that oleic acid? Well, we're also given the density of oleic acid. We have the mass and the density. So the density equals mass per unit volume. This is one of those where you break it into a couple of parts. We know that we need that right there. Okay. So this is an unknown. We know what the mass is. Right. The mass is given as 3.23 10 to the minus 6. And the density is equal to 0.895. 895 grams per milliliter, which is the same as cubic centimeters. So if we solve that for volume, right, the V comes over here and the D goes over there. We divide the D into the mass. 3.23 10 to the minus 6. And divide by 0.895. So that's 3.6089 times 10 to the minus 6 volume cubic centimeters. Actually, I probably shouldn't. I can only use 3 significant figures. So it's 3.61 times 10 to the minus 6. Now that we know that volume, if we solve for height, which is the length of the molecule, then we have volume divided by area. And the volume is 3.61 times 10 to the minus 6 cubic centimeters, divided by area, which is 20.0 square centimeters. So we got, let's see, we can keep 3 significant figures. 1.80 times 10 to the minus 7th centimeters, right? This squared centimeters knocks out 2 of those. So D, 1.8 times 10 to the minus 7 centimeters is the length of that molecule. Kind of short. Okay. So in effect, I sort of worked the problem backwards. I found out what I needed. Right? This is what we have. This is what we need. And recognizing that as a cylinder, and we know what the area is, and we're looking for the height, I have to find out what the volume is. So I ask myself, do I have the information to find the volume? Yeah, I'm given density. So I can find the volume. All right. No writing? I'll wait. Okay. All right, 57. The density of gasoline is 0.7025. 0.7025 grams per milliliter. When gasoline is added to water, what will it do? Float, sink?
Float to the top.
Yeah,
Because the density of water is one.
right. It's a lower density, and gasoline doesn't mix with water. If it mixed with water, it just makes a solution. But since it doesn't mix with water, it'll float. It's like trying to mix oil and vinegar for salad dressing. You can shake it real hard. If you wait too long, it's going to separate, and the oil is going to end up on top because it has a lower density. So A, it floats. All right. 58, here's a practical application of determining density. A piece of zinc with a mass of 12.14 grams. So we know the mass, 12.14 grams, is submerged in 46.3 cubic centimeters of water, or 46.3 milliliters. Right. So we have, let's say this is just arbitrary. We'll say here is 46.3 milliliters or cubic centimeters of water. And after we add the zinc to it, what do we get? We get 48.0. Well, there. So can we determine the density? Mass per volume. We got the mass, that's no problem. 12.14 grams. What's the volume of the zinc? Huh? Yeah, speak up. I'm hard of hearing.
It's about 2.3.
It's the difference between this volume and that volume. Is that what you did? So subtract those two. 1.7, isn't it? Yeah. 3 from 10 is 7. We took 1 from there, so 6 from 7 is 1. 1.7 milliliters. Well, let's use cubic centimeters because this is a solid. All right, so we divide those together, and it should be 7.1 grams per cubic centimeter. We're stuck with two significant figures because that one's 2. Okay. So what we've done is determine the volume of an irregular object by displacement. We're going to do that next week. I think it's next week. Is it next week? No, week after. Laboratory techniques. Next week's exam in chapters 3 and 4. And then the week after that is lab techniques. Today we're going to finish up graphing techniques. Did I do an introduction to that one last time? Graphing techniques? Okay. We'll talk about it a little bit. The boiling of water is what? A physical change or a chemical change? First of all, we got other choices. Did the identity of water change? No. So it's physical change. But why is it a physical change? Because the water disappears? No. The water could disappear in a chemical change too. The physical change that causes the water to disappear is simply that we change it to a gaseous phase in which the chemical identity of the water is still the same. So B is the best answer for that one. And let's see, repetition. Okay, I put this one in here because this figure these figures, 70 through 73. 70 through 73. Let's assess what these figures represent. We know that they're supposed to be types of elements and compounds. The compounds are represented by two different squares or circles, open or shaded, together. Right, that would be a compound. If you have just a single circle or square, then you've got an element. Okay, so A through E. Let's identify what these things are. All right, A, you've got two different elements in there, and they're spread way apart. That means it's a gas. It also means that it's a mixture, a homogeneous mixture of gases. Okay. B is a pure element, right? It looks like it's regularly arranged in its structure. That's a solid element. C is another gas, only this time it's a gas of a compound, right? It's a pure compound gas. D looks like it's a heterogeneous mixture and since it's not regularly arranged, I'd say it's a liquid. So we've got two different elements in there. It's a heterogeneous mixture of elements. Probably a liquid. And E is a regular arrangement of compound and elements. So we've got a homogeneous mixture of element and compound. Okay, now we can answer our questions. 70, which best represents a homogeneous mixture of an element and a compound? E. 71, which best represents a gaseous compound? A gaseous compound. Here, C. 72, which best represents a solid element? It's this one, B. And 73, which represents heterogeneous mixture of two elements? Heterogeneous mixture of elements. Here we go, D. It didn't even care if it was a liquid or not. Does everybody see the representation there in that? Yeah, okay. There again, what we're trying to do is to get you to think on the microscopic scale. This is what you would see if you were small enough. Which of the following has a different value on the moon compared to Earth? Weight. I'm skipping some because it's repetition. Let me see. Oh, there we go. Okay. Which separation technique is based on differences in the volatility of the substance to be separated? All right, we didn't go into a lot of detail on this. This takes advantage of physical change. So if we look at each one, filtration is based upon what? Particle size. Right? You have a filter with small enough pore size, you can filter out this particle size and let the rest of them go through. Very often we use that where we have precipitated something in a liquid and we want to separate it. So we pour the whole thing through a filter and catch the solid precipitate and let the liquid go through. That's not it. That's not based on volatility. Distillation, that's based on volatility.
You have to like heat it up and then it's the lower boiling point goes up.
Yes. And then it goes over and then you run it through your thumper and your cold water bath and you get your ethanol and you can sell it moonshine. Yep. Every moonshiner understands distillation intrinsically.
What's volatility mean?
The vapor pressure that it produces at any given temperature. So at, say, room temperature, you have several beakers of stuff on the bench top. The more volatile one is the one you're going to smell first. Any can of paint by law has to have a rated percentage of volatile organic compounds, VOCs, on the side of its panel. If it's an indoor paint, they're usually water-based latex paints. So it's low volatility. But outdoor paint may have some oils and maybe some xylenes in them to emulsify the mixture before you slap it on your house. They will have high volatile, but you can use it outside because there's lots of space for it to evaporate. So it will have a higher percentage of volatile organic compounds. How about the others? Solvent extraction. What's solvent extraction? If you have a mixture of chemicals and you have two solvents that you mix together, one of them contains the mixture in it and the other doesn't. But the second one in this mixture is lighter. In other words, it floats on the other one. So you have a mixture and you mix them together. You shake them up like oil and vinegar. And then say this is the organic phase and this is the aqueous phase. The organics that are in the aqueous phase are more attracted into the organic phase than they are the aqueous. So they go here like that. And that is that by solvent extraction, you extract the organic fraction from this one into that phase. Then you drain this one out, throw it away, and drain this one out, and then evaporate off the solvent. You got your pure compound. That's solvent extraction. Chromatography. You know what chromatography means? It comes from two Greek roots, graphy, which means to write, and chroma, which means color. So essentially it's color writing. The first paper chromatography was done by a Polish scientist whose name escapes me. He extracted plant matter, leaves, things with alcohol, with ethanol. And then he dotted it on a piece of paper like this. And he drew a line here so he'd know where they were. And he dotted them on the paper like that. And let them dry. I'd let the ethanol. And then he put them in a container with a lid on it. And the liquid solvent only went up to there. It didn't go all the way up to the dots. And it started, as soon as he put the paper in, the solvent started moving up. Solvent front, this thing moves up, moves up, moves up. Goes up the paper. Well, if that's a mixture, which we know it is, like chlorophylls and xanthophylls and carotenes in the leaves, then some of them are more attracted to the paper than they are the solvent. And if that's the case, they sort of lag behind. But the ones that are more soluble in the mobile phase, the liquid that's moving up the paper, they move faster. So they'll be up here. And you can watch them separate over time. You get separate colors.
We do that.
I don't have it planned. Sorry. We're kind of limited on time and resources. But it's easy to do. You can even do it with magic markers. Just take some coffee filter. That would be a good choice. And take some isopropanol from the medicine cabinet. And then take your magic marker. I think black is usually a mixture of something. And then put it on the paper and stick it in there and watch it move up. See if it separates into colors. It's really simple. The method of chromatography has ballooned. This was paper chromatography, the first use of chromatography. And since then, we've got things like column chromatography. I remember when I was taking organic chemistry, we were sharing a lab with graduate students, and they were doing their research project, and they had columns, glass columns that were 10 feet long and filled with a white substance called silica gel. That's the stationary phase, like paper. And at the top, they would take their reaction mixture and they wanted to clean it up so they get the product out that they were looking for, and the rest of it they leave behind. And they put it at the top, and they needed to have a lot of it. So they had to have a huge column. So they put it at the top, and then they filled it with the mobile phase and just kept enough of it up there so it'd keep moving. And sometimes you could see it if they were colored compounds, sometimes you couldn't. So if they were colorless compounds, you would have to do a fraction collection at the bottom. You just have this machine, and every couple of minutes, it'd be dripping into a tube, and it would automatically shift to the next tube. And you go back and keep going. And then you'd have to go in and analyze each tube to find out which one had your compound in it. So that's column chromatography. And then we advanced to high pressure liquid chromatography, which is basically a column that's under extremely high pressure with very small particle size. And I used to operate one of those for the USDA. I also operated a gas chromatograph, where in my case, it was about a 100-meter long tube coiled. And on the walls of the tube was the stationary phase. So the gas, as it moved by, would absorb materials from the gas on the stationary phase, and the ones that stayed in there longer before they evaporated again would be held back, and then the ones that were not attracted to it would move forward faster. And we had options, different types of detectors. Some were destructive detectors, or could have a hydrogen gas flame, and we just measured the conductivity across that flame with a device. Or we'd hook it up to a mass spectrograph, and it would take each fraction, it would go into the mass spectrograph, break it apart into pieces, and give us a spectrum on different ratio of pieces of the molecule. So it's the sky's the limit, right? Mass spectrographs have been mated with all kinds of different analytical procedures. Okay, so the answer to that one is B.
Distillation. Now we're chapter 2. And what do I have? Half hour? Yeah, half hour. I think I'm gonna run over a little bit. Okay, the first people to attempt to explain why chemical changes occur were actually before them. Well, medieval alchemists, the Greeks. The Greeks were first. There were alchemists before the Greeks, right, in the Middle East and in Egypt. But they didn't try to explain why the chemical changes occurred. They were more like cooks, right? They just know you put this together with this together, this, and you get something. The Greeks actually tried to develop a coherent theory of why things happen. So that's E. Now, later on, some alchemists did turn into chemists and bona fide modern scientists, like John Dalton and Isaac Newton. They were both alchemists, but they graduated out of that into real science. 2, the first chemist to perform truly quantitative experiments was Robert Boyle. We're going to look at one of those experiments down the road. We'll actually do Boyle's law here in the lab.
Is that the one with the gold or is that?
No, this is a confined gas. You apply pressure to it and see what change makes to the volume. So B is 2 is B. 3, the scientist who discovered the law of conservation of mass, also called the father of modern chemistry. Think guillotine. Lavoisier, yeah. Got his head chopped off. He was just unlucky. Okay, 4. Which of the following pairs of compounds can be used to illustrate the law of multiple proportions? Remember, that's John Dalton's law. Proust's law is definite proportions. That's a compound from any source, whatever, will always give you the same mass ratios of elements. But the multiple proportion says that if you have a binary compound and you hold one of the elements constant in mass, the other elements will vary by whole number multiples, like NO, NO2, NO3. So you have to have the same elements, the same 2 elements together to take advantage of this law, and one has to vary by a whole number multiple from the other one. The only one that fits that in that group is D, nitrogen monoxide and nitrogen dioxide. Let's see. Nitrogen monoxide, that's laughing gas, I think. Yeah, that's nitrous oxide, laughing gas. All right. Moving on. Okay, 7. A sample of chemical X is found to contain 5 grams of oxygen, 10 grams of carbon, and 20 grams of nitrogen. So we have this compound, and it's been analyzed to give us 5 grams of oxygen, 10 grams of carbon, and 20 grams of nitrogen. Is that right? Yeah. The law of definite proportions would predict that a 70-gram sample would contain how much carbon? The ratios are fixed for that compound. So how many grams do you have now? All right. 35, right? 35 total. So in 35 grams of X, you have
the ratio of 20 to 35, 10 to 35, 5 to 35. So what if we have 70 grams of the compound?
Then it'd be 40 grams of N.
Right, it'd be 40 grams of that, 20 of this, correct?
10.
And 10 of that, right? You just double the amount, you double each one. So the answer to the question is 20 grams. They want to know carbon. All right, 7, 9. Which of the following statements from Dalton's atomic theory is no longer true according to the modern atomic theory? Well, let's see. First one says elements are made up of tiny particles called atoms. That's still true? Yeah. B, atoms are not created or destroyed in chemical reactions. Yep, that's true also. C, all atoms of a given element are identical. We know about isotopes now. And then D and E should be true also. So C is the one that doesn't fit anymore. They've also noticed that isotopes of the same element don't quite react exactly the same. I think it has something to do with the mass difference, right? Because their electronic structure is the same. So that part of the chemical reaction is the same, but under certain circumstances, the mass of the isotope modifies its chemical behavior. Probably how fast it reacts, more than likely. 11, the chemist credited for inventing a set of symbols and for writing elements in the system for writing the formulas of compounds and for discovering selenium, silicon, thorium is, we didn't mention this one. It's probably in your textbook. This was Berzelius. Berzelius was a Swedish chemist. Actually, he did a bunch of stuff. But he proposed a set of symbols that were based upon the first or maybe two letters of the name of the compound, and not always in the anglicized version. Okay. So actually, it's a good thing that Berzelius won because they were competing. Dalton had a system that his system was derived from the alchemists and their oddball symbols. Did I show you that one, that chart with the different symbols from alchemy? Right. Dalton's, I'm glad that they didn't use his because it was a mess. Berzelius was a better idea. So that's 11B. And then 12, Avogadro's hypothesis states that, well, remember Avogadro's hypothesis says if you have two gases, volumes are the same, temperatures are the same, and pressures are the same, then the number of particles in each one is exactly the same. It doesn't matter what the gas is. Okay, so which one of these statements fits? At the same temperature and pressure, equal volumes of different gases contain equal numbers of particles. D. Yeah, D is the best for that one. All right, 13. The first scientist to show that atoms emit any negative particles was. Remember that one? He used a cathode ray tube. He determined the ratio of charge to mass for the electron. J.J. Thomson. J.J. Thomson did that work. That's 13A. 14. Many classic experiments have given us indirect evidence of the nature of the atom. Which of the experiments listed below did not give the results described? Okay. A says the Rutherford experiment proved the Thomas plum pudding model of the atom to be essentially correct.
That's the wrong one, yeah. Yeah, Rutherford's model was the nuclear atom, where the protons were in a densely packed nucleus, and the electrons were out here somewhere.
And was that the one that they deflected? Off the nucleus?
Right. Sometimes it's called the gold foil experiment. Yeah, so 14A. All right, 15. The scientist whose alpha particle scattering experiment, oh, we just named that one. That one's Rutherford. 15C. Alpha particles beamed at thin metal foil may what? Well, let's see, they could go straight through. Most of them actually did for Rutherford's experiment. But a few of them were slightly deflected by attraction to the electrons. And others were bounced back by striking the nucleus. Right? So all three of those are correct. 16 is E. How about 17? Which is one of the following statements about atomic structure is false? An atom is mostly empty space. Yeah, that's true. Almost all the mass of the atom is concentrated in the nucleus. Yep. Protons and neutrons in the nucleus are very tightly packed. Oh, yeah. That's been a puzzlement for scientists for ages. I mean, once we realized the nuclear atom, said, how can you get so many positive charges packed so close together? So we came up with a new force called the strong nuclear force, holds them together. And the neutrons have something to do with that. You'll notice that as the number of protons increase in the elements, the number of neutrons go up even faster. So when you get to really large atoms, the strong nuclear force operates over a very short distance. And the neutrons are instrumental in mediating that force. So when you get really large nuclei, you've got to have lots of neutrons in there to mediate over that short distance. So whereas helium can have 2 protons and 2 neutrons, when you get to uranium, you got 94 protons and 238 or thereabouts total mass. So what would that be? 94 from 238. Well, that's about 120 or so, right? 38. No, 140. In the neighborhood of 140 neutrons to balance the 94 protons. So the number of protons and neutrons is always the same in the neutral atom. No. It is for the small ones, but not for the larger ones. So D is false. All right. Which of the following atomic symbols is incorrect? 20. The way you methodically answer this question is first, I would look at the protons to see if they match, right? Because if you know the number of protons, you know the element, right? Is carbon 6? Yep, carbon 6. How about chlorine? 17? Yep. Phosphorus, 15? Yep. Potassium, 19? Yep. And nitrogen, 8? And 7. All right, so we found our wrong one. That's E. We didn't have to go any further. We just checked to see if the number of protons matched with a symbol. And they are joined at the hip. You know one, you know the other. 21, the element rhenium exists as 2 stable isotopes and 18 unstable isotopes. Rhenium-185 has in its nucleus, right? So there's blue smoke in there. Who cares if it has 2 stable isotopes and 18 unstable? The question is asking for how many protons and how many neutrons. So if you have rhenium-185, let's see, is this 21? Yeah. If you have rhenium,
185, how many protons do you have? You just look it up. Right, let's see, Re75. So you have 75 protons and 110, right, neutrons. 75 from 185 is 110. So D would be the answer. All right, let me make some room here. Point 2, which of the following represents a set of isotopes? Okay. So in order to have isotopes, you've got to have the same element, same number of protons, but different neutrons. So if we look at this Roman numeral 1 through 5, which ones pair up with protons? 1 and 4 with different neutrons, same protons. So 1, let's see, this is 22. 1 and 4, right? And let's see, 2 and 5, 21 protons each with different neutrons. 2 and 5. And then 3 is left out in the cold because there's nothing to match 22. I see 18 protons. Right, that was written backwards to try to fool you. 18 protons is not matched anywhere. So 3 is just left out. So 1 and 4, 2 and 5 would be D. All right, let's see. Let's try 28. What's 28 say? A species with 12 protons and 11 electrons. So we have this 12 protons and 11 electrons.
10 electrons.
10 electrons. Thank you. 10 electrons. Okay. That's going to be an ion because it has 12 positives and 10 negatives. So it's going to have a 2+ charge, right? So 12 protons gives us magnesium ion. That would be C. Right. We have to remember that when you make an ion, you do it by adding or subtracting electrons. Otherwise, you're creating another element. You're transmuting the element. We don't do that in chemistry. You need a nuclear reactor to do that. 29. Let's see, the number of protons, neutrons, electrons in K plus. Okay, we know, let's see, the order is protons, neutrons, electrons. Protons, neutrons, electrons. So we know we have 19 protons. How many neutrons do we have? 20? Yep. If we have an excess of 1 positive, that means we have 1 less negatives. So there should be 18 electrons to give us that 1 positive excess. And E would be the best answer. Those ends need to have little zeros on them. I just noticed that. Because we use N for a lot of things. Later on, you'll see we use N to mean number of moles. 33. Which of the following are incorrectly paired? 33. Well, let's see. Is strontium an alkaline earth? Yeah, it's in the second column. How about tantalum? Is it a transition metal? Let's see, where is tantalum? Oh yeah, it's below vanadium and niobium. Yep, it's a transition metal. Halogen, fluorine's a halogen. Yep. H,
Is hydrogen a noble gas? I don't think so. Right. We send rockets into space with hydrogen. If it were noble gas, it wouldn't react. All right, so D is wrong. 34. Which of the following is incorrectly paired? All right. Is phosphorus PR? No. PR is, where is PR? Oh, there it is, 59. I always get that one mixed up with PA. PR, praseodymium, I think. One of them is praseodymium, the other is protactinium. And I always get them confused. So PR is not phosphorus. Right? Phosphorus is just P. Yeah. Right. So A is the wrong one here. We're doing, yeah, 35. Which of the following is incorrectly paired? All right. Cu for copper. Yep. C for carbon. Yep. CO for cobalt. Yep. Ca for calcium. Cesium is not Ce. Ce is cerium. Cesium is Cs. Right. It's an alkali metal below potassium and rubidium. So that's the wrong one. E. E is the wrong. How about 36? Antimony is Sb. Yep. Sb stands for stilbium. That's antimony. Si is silicon. Yep. Silver is Ag. Argentum.
That's the time, right? It's arsenic, AS.
Yeah, As is arsenic. Astatine is At. Right. It's a halogen. I think it's radioactive too. Yeah, astatine is radioactive. You get more radioactive elements as they get heavier. That's one reason, one rule. The other rule is proton-neutron ratio. So you get Tc, which is technetium. There is radioactive, but it's a fairly light element. Its ratio of protons to neutrons is wrong. Let's put it that way. All right, so E is the wrong one for 36. 37. All the following are characteristics of metals except they conduct heat. Yep. They're malleable. Yep. Ductile. Yes. Often lustrous if they're polished. Tend to gain electrons in chemical reactions. That's right. So E is wrong for this one. All right. Those were quick and dirty. How about 41? Let's see. You're given a compound with the formula MCl2, where M is the metal. MCl2. You're told that the metal ion has 26 electrons. So this has 26 electrons. What's the charge on that metal? In ionic compounds, halogens are always -1. So that's 2 times -1. Is a -2 has to be balanced by a +2. So if it has a +2 charge, it's got 2 extra protons. So it has 28 protons, correct? So 28 protons is nickel. Nickel is our element. E. Let's see. How many oxygen atoms are there in one formula unit of calcium phosphate? 45. Calcium phosphate, polyatomic ion with a 3- charge, alkaline earth with a 2+ charge. So we put the 2 over here and the 3 over there. Right. Okay. So how many oxygen atoms do we have in that unit? 2 times 4 is 8. 8 oxygens. All right, let me make some room now. Forty-seven and 48. Forty-seven. What's the correct name of FeO? Okay. Metal, non-metal? Metal, non-metal. So it's either a 1 or a 2 type. Type 1 is fixed charge. Iron's not fixed charge. It's a transition metal. It's a transition metal that's not it's not silver, cadmium, or zinc. The rest of them have variable charge. So iron has variable charge. What is it? Well, oxygen's always -2 in ionic compounds. So this one has to be a +2. So the name would be iron 2 oxide. How about the correct name for calcium 2+? Remember, when we're naming things in chemistry, we want non-redundant. That's the second one. The first one is, I forget the terminology I used. It's gone. The two rules. Unambiguous. There it is. Unambiguous and non-redundant. Right? So unambiguous would be calcium. But this is an ion. Calcium is an alkaline earth. It only has that one fixed charge. Right? So we don't put the charge number in there. This is a calcium ion, period. It would be redundant to put the 2+ in there. So calcium ion C is the correct answer. Right? B, calcium 2 ion is redundant. Calcium is not an ion. We need to say ion. And we don't say how many of them either. Monocalcium ion. It's just a calcium ion, period. All right, what's the subscript of barium in the formula of barium sulfate? This is 51. Barium sulfate. So we have barium. Sulfate is a polyatomic ion. We know it's a 2- charge because you can look it up on your chart. And calcium is an alkaline earth. So it has to be a 2+. And barium is an alkaline earth. It's 2 steps below calcium. So it's still a 2+ charge. Right? So all we need is one of these and one of those, and it's balanced. So what's the subscript of barium? We don't write it, but it's there. 1. How about 53? What do we got there? Let's erase this. Let's erase 53. It's starting to get weak. The formula for sodium dihydrogen phosphate. Right. Sodium is that dihydrogen phosphate is a polyatomic ion. We write it like this, dihydrogen phosphate. What's the charge on it? 1-. Sodium is an alkali metal. It's always 1+. That's the formula. 1 sodium, 1 dihydrogen phosphate. A is the correct answer. 56. All the following are in aqueous solution. All right, which one is incorrectly named? Well, so these are all acids, right? You see the hydrogen in front. And with, if there's oxygen there, we don't say hydro. So the first one is based upon sulfate. 8 becomes ic. So sulfuric acid, that's correct. CO3 is a polyatomic ion. Carbonate, 8 becomes ic. It's carbonic acid, correct? PO4 is phosphate, phosphoric acid. CN is cyanide, no oxygen there. So ide becomes ic, and we have to say hydro. Hydrocyanic acid. D is wrong. And hydrochloric is correct. So D is the incorrect one. Hydrocyanic acid. Oh, that might have been, was that? No, that wasn't part of Jim Jones Kool-Aid, was it? They used sodium cyanide or potassium cyanide.
Oh, you're talking about the dude that had the cold, he like made everybody drink Kool-Aid.
Yeah. There were like 900 people, over 900 people that drank that stuff and died down in Guyana, French Guiana. And then his bodyguards, his guards, killed a couple of U.S. representatives that went down there to investigate before they could get back to their plane. Okay, 59. That was some years ago. His church was in California before they moved to French Guiana, so you can figure. Which of the following names are correct? Okay. How about sulfide with S2 minus? Yeah, that's the sulfide ion, right? Ammonium chloride. Ammonium is polyatomic ion with chlorine chloride. Now that's correct. +1, -1 balances. Acetic acid, HC2H3O2. Yep, that's correct. Barium oxide. Barium is a 2+ charge. It's an alkaline earth, and oxygen is a chalcogen with a -2. That's correct, BAO. So they're all right. Yeah, they're all correct. I guess you could argue that sulfide. We didn't say sulfide ion. Do we have a choice there? 2, 3, 4? No, we don't have that choice. So when in doubt, pick the best answer. And the best answer for this one is all. Ooh, fill in the table. So some of these are given to us. Symbol, protons, neutrons, electrons. Symbol, protons, neutrons, electrons, and charge. So we're given 206 PB, 206 PB. We're given, that's it. This one, we're given 31 and 38 and 3+. So we have that one, that one, that one, that one, that one, this one. And then, yes. And this one has 5275 and 54. And that one's blank. And then the last one is given as manganese 2+. And we're not given that. We're given this. And we're not given that one. And we're given this one. Plus. Okay. Now we just have to fill in. All right. First one, how many protons in lead? And we're not given it there, so we have to look at the periodic table. 82. Yeah. 82. So we can calculate the number of neutrons. 82 from 206. 124? Yeah, 124. How about the number of electrons? It's neutral.
So it's the same as
Same number. And no charge.
How about this one? 31 protons. Let's see. Let me look over there somewhere. That's gallium. But it has a 3+ charge, we're told. 3+ charge. All right, gallium is interesting. Its melting point is like 35 or 36 degrees Celsius. So you put the solid in your hand and it melts because normal body temperature is 37 degrees Celsius. Use it get some and take it to a party. Wow your friends. Okay, how about electrons? Well, if we got 31 protons and 3 extra protons, that means we only have this many electrons. Right? We're short by 3. This one is 52, which is tellurium. We don't know if it has a charge yet. We have 52 protons and 54 electrons. We have 2 extra electrons. Right? So it's a 2- charge. And the last one, manganese. We look up manganese. 25 protons? Yep, 25.
And then 23 electrons.
Correct.
2+.
There you go. That fills in the table. Now, the next one, that was 61. The next one uses the same logic, so I'm not going to go through that one. Write the symbol for each one of these. Okay. All right, 63. Silver, argentum is Ag. Calcium is Ca. Iodine, just capital I. Remember, when you only have one symbol, it's always capital. When you have 2, it's capital little.
EU.
Copper is Cu. Cu. Cuprum. And phosphorus is P. All right. Name these compounds. FeSO4. Remember, this is a type 2 metal-on-metal compound. So iron has to be specified for its charge. Sulfate is a 2- and you only have 1 iron, so it has to be a 2+. So iron 2 sulfate would be the correct name. C2H3O2 is a polyatomic ion called acetate. It has a -1 charge. Sodium has a +1 charge. And this is a type 1 compound because it's sodium. Sodium only has 1 possible charge. We don't have to say what the charge is. So if we say sodium acetate, that's non-redundant. And that word I can't remember. Unambiguous. There we go. I need to write it on the board in case I need it again. Unambiguous and non-redundant.
Pretty much just means it doesn't repeat itself. Right?
I'm sorry?
Non-redundant is pretty much like it doesn't happen over and over again.
Right. You don't put information in there that's not needed. So we wouldn't say sodium 1 acetate. We know it's only a +1 charge because it's sodium. KNO2. NO2 is nitrite. K is potassium. Right? It's a type 1 compound. Plus charge, -1 charge. We just need 1 of each. Potassium nitrite. Calcium hydroxide. We don't have to say what the calcium charge is because calcium is an alkaline earth. Hydroxide is a polyatomic ion, OH-. We need 2 of them. So that's why we have a parentheses with a subscript of 2, because the polyatomics have a charge on them, but the charge is distributed over the entire group. So you have to have the parentheses. Calcium hydroxide is the name. NiCO3, Ni is nickel, and it's a couple of different charges are possible. So it's a type 2 compound. You have to say what it is. So that means you have to calculate the charge. CO3 is carbonate, and it's a 2- charge. You've only got one nickel, so it has to be a 2+. So nickel 2 carbonate is the correct name for that one. All right, I kind of got chopped off there at the top. NO3, nitrate is NO3. With a minus charge. That's what it should be. Aluminum oxide. Aluminum is a fixed charge metal. 3+. Right? So if you say Al 3+ and then O 2- together, 2 comes over here, 3 goes over there. Al2O3. Ammonium ion, NH4+. That's the only positively charged polyatomic ion in our list is ammonium. Perchloric acid. Here we work from what is perchlorate? ClO4-. Make it an acid. That's perchloric acid. 8 becomes ick. Copper 2 bromide. So copper has a 2+ charge. Bromine is a halogen with a -1 charge. So we need 2 of them. Okay. Then we go the other direction. All right, we take the compound and name it. All right. Aluminum is a fixed charge. Aluminum sulfate. If this was England, it'd be aluminium. Ammonium nitrate. That's it. We have 1 ammonium, 1 nitrate, 1 positive, 1 negative, and 6% fuel oil with a blasting cap, and you got yourself a nice bomb. Sodium hydride. Right? It's not hydroxide. There's no oxygen in there. Hydride. You say hydrogen, change the ending to IDE. All right. You have several of those. Metals combined with hydrogen. Aluminum hydride, I can think of. Lithium hydride. Potassium hydride. Lots of metals combined with hydrogen in that way. Potassium dichromate, CR207. Whenever you see an oxygen, you've got 3 or more elements in a compound, and there's oxygen's one of them. Suspect polyatomics and go looking for them. CR207 is dichromate. It's a 2- charge, so we need 2 potassiums. And potassium is an alkali metal, and it's only got a +1 charge, so we don't have to say what it is. It's just potassium dichromate. That's it. Carbon and chlorine, those are both nonmetals. This is a type 3 compound, which means you just say carbon and then how many chlorides are there? Carbon tetrachloride. Tetra for 4. Silver chloride. Silver is one of those transition metals that has a fixed charge of +1. So we only have to say silver chloride. That's it. Calcium sulfate. Right, we got a polyatomic ion there. Calcium is a 2+, sulfate's a 2-, just 1 and 1. HNO2. So here, since we didn't say it's an aqueous solution, you could name that hydrogen nitrite. But if it's an aqueous solution, it's nitrous acid. Ites become us. That's why I named it that way. But I have given credit for hydrogen nitrite since I didn't say it was aqueous. N2O3, 2 nonmetals, dinitrogen trioxide.
What would make it aqueous? like to go with aqueous.
Which one?
The last 73.
Oh, you would say this. Just like that. That would mean it's an aqueous solution and you name it with the acid convention. And then the last one, tin, is not a transition metal, but it's one of those that does have multiple charges. Right? Tin is in the carbon family, but it's down below that heavy line, which means it's in the metal region. So that metal is either a +2 or a +4. And in this case, it's a +2 because it only has 2 iodines with it. And, oh, there's more. S2O3 is thiosulfate. And it has a 2- charge, so we need 2 sodiums to balance it. Iron 3 oxide. So in that case, you have iron with a 3+ charge, and we know oxygen is the 2- charge. So we just put the 2 over there and the 3 over here, Fe2O3. Dichlorine heptoxide. We just say Cl2 for dichlorine and 7 for hept oxide. Cobalt-2 chloride. Right. Chlorine is -1, cobalt. We know cobalt is 2, right there, it says so. 2+ cobalt, so we need 2 chlorines. Hydroxide is a -1, aluminum is a +3. So we need 3 hydroxides. Sulfurous acid, right? I probably should have written it like this. H2SO3, because it's derived from sulfite. Sulfite, ite becomes us. Sulfurous acid, I should have written this, but I will accept that. Nitric acid, same thing. NO3 is nitrate, 8's become X, nitric acid. Phosphoric acid, PO4 is the phosphate, and it's a 3- charge, so you need 3 hydrogens with it. If hydrogen is in a molecule in the beginning, it's usually assumed to be a +1. If it's with a metal and a hydrogen, it's usually -1. Okay, because the metal comes first as a positive, the non-metal comes second as a negative. So that in that case, hydrogen is a negative. Acetic acid, I wrote it 2 different ways here. The accepted way is HC2H3O2. But in older literature, you might see it written CH3COOH. This gives you a little information about the structure. If we draw this structure out, we have carbon here, 3 hydrogens, then connected with this carbon, and then we have an oxygen here with a double bond and an OH here. This is the acidic hydrogen. That's the one that dissociates and makes the sour taste in your vinegar. That's the only reason I wrote it both ways. Phosphorus trichloride, 1 phosphorus, 3 chlorines, PCl3. Oh, more? Okay. 86. Which of these statements is a consequence from the law of definite proportions? Well, let's see. All samples of chlorine contain 35Cl and 37Cl. No, that's isotope ratios. Right? That's how you would calculate the atomic weight, average atomic weight of your element. No, it's not that one. Mass of oxygen that is combined with a fixed mass of nitrogen in each of the binary nitrogen oxides can be expressed as a ratio of small whole numbers. That's not definite proportions, that's multiple proportions for B. C, the atomic masses of all the elements in a periodic table have fixed values. No. And they're not even fixed, actually. They're fixed for now, but the next time a periodic table comes out, they'll change. It might be in the fourth, fifth, sixth, or seventh decimal point, but they'll change. D, the percent lead by mass in a compound galena is the same for all pure samples obtained from any source. That's it. D. Definite proportions. 87, multiple proportions. Okay, in multiple proportions, we went past that one. B, right? For nitrogen oxides, the ratio of the oxygen for each of the compounds is whole number multiples. That's multiple proportions, 87. Which of the following elements does not have a symbol taken from the Latin name for the element? Fe for iron, Cu for copper, Na for sodium. Those are all Latin. K for potassium, titanium, Ti. That's not from a Latin source. Which of the following ions is not likely to form from their appropriate atom? Well, let's see. Sodium is +1. Yep, it's an alkali metal. Titanium is 4+. So look at, it's a metal, so it's probably going to be a plus charge. But you can look at your periodic table and see that +4 is one of those possibilities. Magnesium is always 2+. Arsenic 3-. It's in the nitrogens, the pnictogen family, and those in ionic compounds, they're always 3-. Right? In covalent compounds, in compounds that are non-metal, they don't have a charge. So they can only be charged when they're combined with metals. Carbon 4+ is highly unlikely. Let's see if they put that. It's the last one. It's possible you can get a 4+ charge of carbon, right? Because carbon is, well, let's see, we haven't done electronic structures yet. I'll save that for later. So carbon is the most likely answer. Not likely to form from the appropriate atom. It can form, but it's not likely to. How many protons, neutrons, and electrons in the order are present in anion formed by one atom of iodine? When it says anion for iodine, right, it's 125. And iodine has 53. So that the anion formed from it is always just a -1. That means that many protons, 54 electrons. Neutrons then would be, did it ask neutrons? Yeah, neutrons. Neutrons would be 72. Right. So protons, neutrons, electrons. 53, 72, 54. Yeah, D. It just keeps going and going and going. Like the Energizer Bunny. Just won't stop. Which of the following atoms, isotopes, or ions contain 23 protons, 18 electrons, and 27 neutrons? Okay, 23 protons would be vanadium, correct? Okay, so that's 23 protons. If it has 27 neutrons, that means 50 up here, right? Yeah, 50 up there. And the charge, if it has 18 electrons, the difference there is a +5, isn't it? So 50 + 5 and 23 for vanadium is C. Okay. So which of these is incorrectly named? Magnesium hydroxide. You don't need the dye. That's redundant. You know you have two because hydroxide is a -1 charge. Magnesium is always 2+. So you need two hydroxides. Magnesium hydroxide is all you need. That's the wrong one. You can assume the rest of them are correct. That's it.